Alright, so this is number 6 on your worksheet. Basically, it's a guy, there's a block on the ground. It's 20 kilograms. And someone lifts this block 1 meter high. Okay? So that's the 20 kilogram block after it's lifted. And your system for this problem is the box and the Earth's gravity field. And we would say that the person's doing work on the block. It's not moving in the beginning or the end. So they're doing work on the block, and that's why there's energy there's gravitational potential energy in the end. So work is going to equal U grav, right? So work is going to equal to mg. Maybe I'll call this delta H, so mg delta H. So work is going to equal 20 kilograms times 9.8 newtons per kilogram times 1 meter. And notice I get 196 joules of work were done on the box. 196 joules of work. So this is the work done on box. And it's also the energy transferred to Earth's gravity field. And then while lifting 20 kilogram box 1 meter in height. Okay, now I'm going to do number 7 and we can compare those numbers. So number 7 is a bit different. Number 7, you've got the same 20 kilogram blocks, but you're pushing it up a 30 degree angle ramp. Still the same height, 1 meter, right? And force diagram for the box would be weight, normal, and then the force of the person, right? So I'll call FP, I'll call F grav, and I'll call this one normal, right? And some reference lines would probably be helpful here. So you'd see that every other angle is this 30 degree angle. So that one, this one, this one, and that one. Those are all the same 30 degree angle. Okay? And then the vector sum diagram, you'd have your mg, you have your force due to person. Actually, I don't like that one. I'm going to redraw that one. Person's pushing more like that, right? And actually, I'm going to redraw that one too. So normal is going to come up like that. The force of person will be maybe like that, right? And you can see that this angle here on my diagram is this angle here, right? And this force here is mg. This is force of the person, and this is my normal, right? And we were told that, by the way, that this is a frictionless ramp, okay? And if you want to find the amount of force required now, force should be a lot smaller. After all, you're using a ramp. And sine would probably be a nice way of doing that. Sine of 30 degrees is going to be force of the person over mg, right? And so the force of the person is going to be mg sine 30 degrees. Force of the person, therefore, will be 20 kilograms times 9.8 newtons per kilogram. That's our gravity field. Sine 30 degrees. So that's going to get me about 98 newtons, right? So this is the force to push box up ramp. And it's a frictionless ramp. Now, we also want to use this same triangle, and we want to figure out how far the box would go so we could calculate the work. And it's still 1 meter high, and this is still 30 degrees here. So let's see, sine 30 degrees is going to be 1 meter over L, solve for L. L is going to be 1 meter over sine 30 degrees. That's 1 meter divided by 1/2. That's going to be 2 meters. So that's the distance of the ramp. This distance here is 2 meters that the block gets pushed. So now we could find the work done. So the work done on the box while pushing it up the ramp is going to be the force applied that's parallel to the distance it moves, right? So that's going to be 98 newtons applied over a 2 meter distance. Whoa, wait a second. This is the same thing we got in the previous problem. So this is number 7. The previous problem, number 6, we just lifted the box, and you can see that the same work was required. But since the distance is doubled, the mg, the force you would have to push up to lift, should be cut in half, right? Because mg is going to be almost 200. And now you'll notice since we push for twice the distance, we're now cutting the force in half. But the energy or work is exactly the same as it was before. Anyway, I hope that helps. Hope you have a good day and good luck tomorrow on your energy test. Bye-bye.